hopefully you're not too tired yet, because now we are going to talk about performance and detecting bad performance, because Nikolay Mitikov has been hunting for bad performance crimes for over 8 years. He's an application performance detective and Sitecore MVP, and just a few questions that he's going to answer in this presentation are how to figure out why apps are slow, how to figure out the data causing code to be slow, how to make software work faster, how to understand that we actually made it faster, and other how to and how to not. So a round of applause for Nikolay, the performance detective. Off you go.
Hi folks, the pleasure is mine to welcome you on Making It Faster Talk. Like a few words about me. My name is Nick. I am chasing performance and stability crimes for last 8 years or so. And I blog about my investigations and performance crimes in here. Why the rocket is here? Could you imagine that 50 years ago people were able to send men to the moon? And still we are experiencing slowness in our apps. Let me drop a simple comparison with a car. Do you need to know how the combustion engine works in order to drive the car? If your engine is faulty or not performing well, would you fix it on yourself, or would you drive it to the service station? Previously, or would it be fair to say that only F1 teams would have their own service teams who would service their cars, making them faster? And that's what we do in CPH Mist. We do hosting, and then we enable our customers with the performance. So, what's our agenda for today? We'll have a lot of memes and a few questions to get started. How many of you are familiar with the .NET? Maybe I can see a few hands. Cool. JavaScript? A few, cool. Silverlight, anyone? There was such technology. Okay, ActionScript? Okay, there was technology as well. So, frameworks evolve, code base changes, and technologies are born and decay over time. However, the foundational ideas, they remain. I would like us to have an easy-going talk on ideas rather than principles. I will showcase a few easy examples on .NET, but it's fine, readable, whatever, if you even don't know the .NET. We'll be touching agenda points in a few slides. If you're here wondering about the performance, I should not be throwing such arguments as stability cost a fortune and lead to frustration. Basically, that's a big fish in the sea, and that's what more to, from my personal experience. One of the customers had a network split, their solar cloud died, and they lost money. Before jumping further, I would like to take a moment and ask you specifically, why do you think that software should be fast? Google would say that slower sites lead to less conversion, but what's your take on that? It roughly takes 7 seconds for a human being to form a first impression. It's so hard to change then. To me, performance mimics the implicit owner's attitude towards customers. That is like the effect that I see, is my time, efforts respected or no? If we agree that software is at least desired to be faster, then how to make faster? The first step logically would be to know where it slows down and how to understand where it slows down. Assuming there is a mechanism that can explain us what does every thread in your application do every millisecond, meaning we can see that this guy takes a lot of time, wide. How to figure out that we actually can do better with the data that application operates, right? There was another guy just like you writing the same code, and he put his heart and soul to make it fast, and you are trying to overcome that and make a better version. We'll touch this point and this point. There is a super accurate mechanism that could tell us how the code is executed, and we can test different versions in simple language to know for sure with the same set of data which one is faster. And maybe we'd like to know why it's faster. Assuming there are a lot of tools to see how the hardware is being utilized, what could we do if it's actually third-party framework, enterprise framework that we have no source code access? We cannot just recompile it, whatever. Is there a way? I would take you to the crime scene. We'll try to discuss the methodologies, and then we'll try to see what it takes to write fast code. So we received a complaint on September 26. It's quite fresh. That site is slow. As you can see from the chart, the story ends well. Just in a few days, the performance was improved noticeably. We haven't received a complaint on CPU, RAM usage, or anything like that. Take a moment and think, please, what would you do in this case? How would you decide to resolve this problem? Because that's all we have for now. I have even a few options for you. We can get a bigger box, only CPU. Then we know that when CPU gets hot, it emits a lot of heat, and then it starts throttled. So we might want to update the cooling system. Storage, add more servers, add less servers, put less servers closer, put far servers, whatever, everything. We can switch from SQL to Mongo, from Mongo to SQL, use microservices, use Kubernetes. And here we land with first set of techniques for performance investigation. The first one is called random change. The idea is that you don't measure anything. You just pick random attribute to change, like cache, CPU, like monitor refresh frequency, change it one direction, and then you make yourself confident that it helped. You spread the confidence around people that it helped. And the statement made by a professional with high level of confidence works. You're going to be wondering how come it could work. How many of you have heard about Daniel Kahneman, the guy who won a Nobel Prize in economy for finding bugs in humans, in human perception to be precise? So guessing, no. Another technique that is quite popular, blame someone else. You are doing one part of the system, and then there is another service you're talking to. There is a performance problem, and you find evidence, not really evidence, that the problem is with that component. You reach to that team. Here is a real-life story from a few weeks back. The server was experiencing high CPU load randomly with no traffic at all. And there was a memory snapshot collected. In the memory snapshot, there was Redis timeout exception. And the guy said that Redis timeout exception, that's the problem. That's why it doesn't work. And then the team that manages Redis saw that we haven't received any traffic that time at all. The problem was actually in critical section inside the CLR, internal implementation detail, so it had nothing to do with either of those. So blaming someone else, it's not the way to go forward. Street light anti-method. So the guy stands next to the projector light trying to find the car keys. Another one approaches him, asks, what are you doing? He's like, I'm looking for the keys in here. They're looking together for a few minutes. The guy asks, are you sure you've lost your keys here? And he's like, no, I've lost them there. But why are we looking here? Because the light is here, man. I believe if you are developers with some sort of experience, you have at least tried or was asked to solve any problem in the world just by looking at the logs. You've been supplied the logs and they can answer any question. And the last method for today would be traffic light anti-method. Big system, enterprise system, they usually have monitoring systems. And if monitoring system says that everything is fine, then everything is fine. Why to worry? So, no, that's not the way we want to do performance investigations. We want a solid approach. jokes aside, how to do it the right way. No random changes, right? After the problem statement is defined, we should try to land with initial hypothesis. What's happening? Then we need to make a prediction, like if that's the problem, then we could test it by that way. We could measure the results and repeat, right? For example, our page loads slow because cache sizes are too small. We can increase the cache sizes and page would be loaded faster. But wait, how do you land with initial hypothesis? We need to narrow down the list of questions or the culprits to know. In our performance crime, has this system ever performed well? Yes, it was performing well, but over time it started to slowly degrade. What was changed recently? Nothing. Can the performance degradation be expressed in terms of latency or runtime? Yeah, you saw the chart that there was the percentile 90 slow for time to first byte. Does the problem affect other people, applications, or it just you? It was noticed that the main delivery center or servers are in Europe, but actually in other regions where they have small subset of servers, it loads faster. What's the environment? We're going to be using Azure Web Apps in here. And today we'll be looking at 3 performance methodologies. Use, first one is similar to plain emergency landing guide, a set of steps that you could do. I think you actually do that. Use stand for usage. For every resource in the system, you see how busy is that. For example, you've got CPU that runs on 95% for 10 seconds or for 1 hour. Saturation means like, do we have the resource that fills over its capacity, runs over its capacity? You get some sort of queuing in there. And E stands for errors. The next one would be event tracing. When we look at the system dashboards, whatever, we get requests per second in average or just aggregated stuff. We don't get the detail of every specific request or every data bit that enters your system. However, sometimes that data is crucial to figure out what's happening inside. And latency analysis. We know that this is the pile of time it takes for an application to do what it does, and actually where it arrives from. What is happening in this slice, this slice, this slice, every slice. We need to understand what happens everywhere. And how it looks from inside, how it looks from outside. You could think that there is a person, that your customer, and then this is your server. And they're connected directly with a wire. But that might be not the case. So the person is here, your server is somewhere in here, and there is also the distance in between. Question out of blue. You have arrived in here from different countries. Do you know how much time would it take for a signal, like ping, from here to your hometown? Because that's the time of spending here. So we've briefly covered main techniques that we're going to use today, and we could enter the crime scene again. We are armed with performance investigation techniques. Let's see, can we find the bottleneck or no? That's what we've got, and we're trying to see from one end to another end what's happening, or end-to-end transaction stuff. I'll try to guide you through in here. So on top, it says the heartbeat. So basically, this is the system probe that we saw. Homepage, nothing fancy. And this page for sure has been requested previously. In here, it says also the Australia, so it's not in Europe. The health probe arrives from, or probes, SIA region. And you can see quite a number of dependency. It's SQL calls. So we're looking at a site that used to perform well, and then all of a sudden, we could see for random request, it takes over 70 SQL queries to load. And nothing seemed to have changed. That was repeated for different requests, and we would see the same pattern all over again. And I'm not sure if you could see it on the screen in here, but there is also a gap. Like you get the waterfall of queries, then there is a pause, and then another waterfall. How trusted those measurements are? Can we prove them? Remember, that was not in our location, that was elsewhere. And yeah, we could use web page test. There is a tool or a site that allows you to test page from different locations. And what is important in here, that we are adding a unique query string in here. Nikolay checks. Yeah, so that's how it can be seen from the client itself in there. That's the movie Ford versus Ferrari. Christian Bale gives an awesome performance, like drives perfectly. And a few moments after the race is finished, he knows how to make his car faster. Because in every single moment, he exactly knew what's happening inside, like brakes are doing well or no, what about engine, so what could help us to make that sort of improvements? Dynamic profiling can show us what's happening inside. There are so many profilers in there, and we'd like to pick the one with following criteria. It doesn't need any sort of installation, it's easy to use, minimal overhead, and we could extend with our own events or data that is specific to our application. And luckily, OS supports such a thing as event tracing. Basically, you can emit events, a lot of events, super fast. You can enable them or disable dynamically. And you can also extend it. And same true for other. The tool we're going to be using is the Purview. It's the tool built by Microsoft, actually by one of the Microsoft performance architect, Vance Morrison, to prove that it's not the .NET that's slow, that it's actually the code that .NET is quite fast. So easy to use, just 2 steps. First one, you download it, they build it for you. And the second one, you just select a few checkboxes that you want to see the thread time, what does each thread do every millisecond. You want to pack everything into one bucket, and you don't need UI to do that. There is a command line collection tools. In here, you want thread time with low priority, and you collect it for 80 seconds. In Azure, you have limited access. Could you do that? Yes, they have that profiler embedded that would collect event traces as well. On that slide, you might have noticed some weird IDs. What are those IDs? The event tracing model is quite extendable. You can write your own providers, anyone can. And there is a set of providers that arrive out of the box for you. You just can ask what is there, and then you could turn on specific provider that you're interested in. Explain what is activity ID before we proceed. Okay, so the data arrives to your application, and it should be tracked throughout the whole state of application, like microservices or whatever, should be traceable, that you know that this is the data you are dealing with, and in this moment you're dealing with the same data. So basically that is the operation identifier, somehow, whatever. In here we could see important part that are highlighted. Session ID, meaning that it's a shopping cart that only one person at a time can drive. If multiple can drive, then it crashes. So basically there is a system that controls the access. And Azure reference, that's the front door stuff that enriches the original request with this specific header that can be traced throughout the system. But what if I need to add my own events in there? Is it possible? Yes. At the same repository where Purview lies, there is the event trace library from Microsoft, and it is easy to use as that. 2 lines of code. And then, boom, you just call log something. And it runs on events, not on anything else. And you can open it in Purview and see your events in here. Question: how expensive could login be in terms of performance? Make a bet. Make a prediction. TrueLife, one of the apps I was looking in, spent half of the wall clock time just doing log debug or log info. So it's kind of expensive. And then if we get millions of events, how am I supposed to aggregate them? It's quite easily. When you collect the profile, they're embedded, and in the beginning of the trace, there is a structure of the event, so you can just ask per few or whatever to generate the manifest, basically, so that you could do this stuff, right? Strong typing. Event tracing is OS feature. What about containers and the rest? Luckily, for at least 3 years, you could do that easily. And then if you try to launch it in a container, nothing will happen. But that's a gotcha. It will seem to do nothing, whereas it was doing something. You don't see what it was doing. Good move, good move. But that's only the part of the puzzle. You see that this part takes a lot of time. Maybe that's the best algorithm could be written in there. And just by seeing the timing without the data it operates with might be useless. And sometimes you don't know the full set of data that your application operates with, so you need to know not only the parameters that your method called, but everything surrounding the cache state or whatever. So it's unrealistic to use events to record everything. And ladies and gentlemen, memory snapshot. On your right there is a memory snapshot, on your left there is a picture. Or the opposite way around, because actually it's just a sequence of bytes together, right? What can it show us? Everything that is inside the application, your objects, your threads, what they are doing, call stacks. Maybe you can see some sort of queuing in there. Similar as if we look at the picture park, you can see that the tree bends, but you don't know for how long it bends or what's the wind speed. You can roughly guess, but you cannot get the full motion and therefore speed. So it's basically an indication of the state itself. Very easy to create, either through Task Manager or you can use the program tools, basically command line stuff, or in Azure you have diagnostic tool that can collect it for you as well. And that's sample output. We see that a lot of objects in here, and a true life story about the MongoDB that it will get 1 million of objects that are pretty much useless just because the way it was coded, the driver itself for the C#. The next question is that we've got millions of objects. How are we supposed to extract them and what would be the purpose? There is a library that can treat that sequence of bytes, translate it into entities. Basically, if the CLR knows how to put our objects into memory, there should be a translator that can do the opposite way. On your left, this is how the memory looks like, and on your right, this is the code that parses it. And what are you supposed to do with the data? You could write a benchmark using the benchmark.net, for example, and then you could use the data on top that you have just exported to see which version is faster for that specific application that you're investigating. So it's not the synthetic data, just what it runs with, and the slowness is there. And you can see the results. You can see even the memory, how much memory was allocated, like a lot of stuff. And the next one, how can I see why one code is faster than another one? That's an easy example. In here, we have two classes or two samples that do exactly same. It's the counter implementation. The only difference is that allow connect check is moved from here to the very beginning. What's your bet? How the performance shall change in multi-threaded in high-performant environment? And we can actually use the profiler to look how the hardware is used. There was the compare exchange statement that would allow or forces the memory to be refreshed, the fresh value read, then whatever. So that is kind of slow. And then there is another version that doesn't do that. In that case, performance counters were not allowed to be used in the system, but that check was lost. So anytime you wanted to increment the performance counter, you expect it to be very fast operation, but it killed it, basically. Also, I'd like to pay tribute to Bartos. This guy explains or gives examples on how the code, like when you code it, it's translated into IL code, and that IL code is translated into assembly that's actually executed. And he finds not the bugs, but interesting edge case scenarios when you wouldn't expect it to happen. The next question would be, if we get billions of operations performed every second, like a lot, how can we be sure to collect in the right point in time when we're interested in? For example, I'd like to know everything in this specific time. And as I mentioned, there is a way of command line collection. And then you can collect the memory snapshot in exceptional situation. But there is no exception. You could raise one, right? But if you don't know the code, it's a third-party framework, any driver you could think of, or any system you're talking, whatever. The logical question is, if there is a text file, it holds the content, and you can modify that content directly by changing the symbols, just because the format is known. Would there be a way to modify assemblies in the same fashion? Because basically an assembly is a sequence of commands in here, and yes, we could, just by doing that stuff. Recap what we did so far. High-level questions to narrow down the suspects. We checked some historical data, saw what was happening, a lot of SQL calls and some pauses in the middle. We didn't do any guessing. We didn't jump to scaling servers up, down, databases, whatever. And we've also were able to prove that it's actually happening in there. We have turned on the profiler to profile what system is doing. And also we collected the memory snapshot to see what is happening inside the process. So roughly these are the steps. With a unique identifier on the client request, we could see what's happening in our server. And then with the snapshot, we could enrich the data, whatever we needed. So we have received a holistic view of the whole system or specific request processing. That's just an example that for one of the systems, the DNS lookup took a lot of time for remote locations. That's not for this system. We have already discussed that there are a lot of events, right? And let's see who are on top. We got a bunch of requests that are waiting for a card. How that could happen? Event tracing is enriched with certain information, and one of the headers holds the client IP address. We check, and it turns out that it's sort of spam. So these requests are irrelevant. We can block that IP or whatever. The next one would be the homepage, right? And we can see that it takes 1.5 seconds in here. Let's see what happens. I will highlight the stuff. This column include, it tells how much time is taken by me or any of my children whom I call. And it turns out that resolve pass, meaning that you type in URL and just to map it to an entity, it takes roughly 45% of the time. Then the next line would be cache. We remove a lot of things from cache for 20% of the time. And then we do SQL queries for at least 18% of the time in here. We can see the call chain that they are connected together, that the resolve pass invokes SQL query. And this is the code, if you can see it from here. On top, we try to get it from the cache. If it is in there, all good, but eventually it's not good in our case. And we try to resolve it. It's the recursive function that calls itself, but at some point in time, we get the value in here, and we try to restore the data that is mapped to this identifier, whatever, and it fails, and then it provokes the cache cleanup. Once the cache is cleaned, we get child by ID, so another SQL call. So random point in time, similar for other times. Why mapping cannot be resolved if that's the code in here? The only idea that I have in my head is that data was removed, but come on, 70 times and for any request? Nah. We need to inspect the content of the cache in memory. Remember, we took the memory snapshot, then we wrote the code to extract it, and then what we observe in here. On our left, we see that we get sort of null object pattern. When we know for sure that an item doesn't exist, instead of doing the lookup or resolving option, we would just tell that it resolves to null ID. And the code itself tries to map that identifier to data, cannot, and then boom, clean stuff. If that is the only method, or who could also put the data into the cache? We can see that there is sort of another guy that uses this method, but it is obfuscated. So obfuscation, basically you write something, you don't want people to know what you're doing, and you try to hide your code. Logically, there should be a way to revert that operation, right? And there is the obfuscator. So let's try that guy, run through, and see what happens. So in our case, indeed, there was an ID object put in there. Done. The next part would be, what does it take to write fast code? We found the bottleneck, and how could we do better? Quiz. How many CPU cycles do you think can happen, like when you do the file request? I can give you a hint. It's useless, right? The problem is that people cannot scale the numbers they cannot understand. But if we scale it to a seconds, let's say if one cycle takes 1 second, then solid state disk takes from 9 hours to 90 hours. That's a lot. So the next time you're going to be coding request to third-party system, you're going to be asking, should I, for example, cache responses from the Solar, because it's so close? Just reaching outside the process takes a lot of time in terms of processor. Understand the technology limits. Question. What percentage of hardware would your language effectively use? What does it mean? You have this certain processor frequency, but then there are assembler commands that are executed in different registers, they're implemented differently, and basically that would be it. That is MIT course of performance engineering of software system, and the table as is of 2018. What is important in here? That even with the best of breed optimizations, it can take how much faster could it be? Like a lot of time faster, right? But out of the box, you don't get that performance. Next question. how faster the technology you work with, the earliest version you have worked with the version you are working or up-to-date version. At least .NET 6.0 looks very promising. Next one. What can be faster than spending a few CPU cycles? We saw that CPU cycle is considered to be one of the fastest. Actually, not spending, right? But the most important part, according to John Bentley, the computer scientists, would be clean design and implementation and maintainable modularity. You might have expected a golden gray like sort of performance trick to highlight, and I sense you might be not impressed. I could try to explain this point. As the system evolves, you'll get bottleneck in different places. And when you resolve one bottleneck that was slowing you down, you'll get another one. And there is a falling tree. What are the chances that you don't see any falling trees for the rest of your route? So you will need to change everything, like algorithms, databases, structures, technology, whatever. The easier you could do that, the less restricted you are, the safer changes, the easier for you to implement it, the better. And if there is only one thing you could take away from this session, I'd like it to be not jumping to conclusions without technical facts. I've seen so many cases when people observe the slowness or the stability or the perform whatever thing, and they straight away do the scaling or increase cache sizes, jump to some certain actions without actually understanding what's happening inside the system. And a few QR codes that I would like to suggest or promote. The first one is the book from the guy who is on the Netflix, The Performance Architect. Another one is study from Louis Bentley, the course that I've mentioned, and also the dynamic profiling course from Vance Morrison. So that would be it. I think we made it slightly faster.
Yes. So, detectives, are you ready now to make it all faster? So, okay, let's see. Thank you very much for the presentation. Let's see if we have any questions at Pine. Do we have any questions here in the audience? I'll try to see. Looks like no, and looks like that in the Pine there is also no questions this time. So that might mean one thing, that the detective is free to go, and we are free to go. It's all good. So thank you once again. A round of applause.